So you probably have seen this in previous videos. We have a data set here that we are going to use for training. We assume this data set is best represented by a line, the weight times x plus b. I suggest, if you haven't seen this before, to go back and watch the previous videos that you can get to from my playlist that I will put in the description. So please head over there and watch the previous videos so that you can come up to speed. So during training, as you can see here, every data point has well-defined coordinates, x and y. And we need to calculate the weight and the bias for a line that may be best fit for these data points. So the line may start somewhere here. Why? Because we are randomly selecting the weight and the bias. It can start somewhere in two-dimensional space. And then what do we do? Let's take just this data point. This discussion will apply to all the other data points. This data point has the coordinate x1 and the actual value y as output. But according to the initial line that has the specific weight and the bias that we selected initially, this line says the coordinate for this data point is really y hat at initial training. And again, this line can be anywhere in two-dimensional space. So the loss, as you can see, y hat, which is the predicted value by this line, is way off, is very different from the actual output. In the previous video, we described the loss to be y minus y hat squared. And this is for only this point. Now, we described in the previous video that the total loss or the cost or the average loss for all these data points, essentially you're doing exactly the same thing as we are doing for this data point, is described by this equation. So we are summing up all the losses for all the data points used in the training and then dividing the total by the number of data points. The loss is really a function of the weight and the bias, because the weight and the bias will be changing as we are training. So the loss expanded. So we are replacing y hat with the value w times x plus b, as shown up here. And we need to minimize this. So you can imagine during training, as we change the weight and the bias, that this line will move closer and closer to be a best fit for this data set. Eventually, we'll find the best fit line for this data set. And you can see now for this data point, the y hat is much better than the y hat we had at the initial training. So we minimized the difference between the actual output and the predicted output. So how do we do that? So I just shared with you visually that the line will move through space as training continues so that we find the best fit line. If you look at this loss and you expand it, it's really, and you plot this loss against just the weight. Now, I mentioned on the previous slide that we have a bias too. But to simplify this visualization and this diagram, let's assume the bias is zero. But everything that we'll discuss here will be applicable to two-dimensional space and more. 3, 4, 5, 6, a million, a billion dimensional space. This discussion will still apply. So I just simplified this diagram so that we can grasp this concept much more easily. So we plotted the loss against the weight. The weight is changing, as we said, because we are trying to find the best fit line by changing the weight. So the loss is really a parabola versus the weight. We start with the initial weight randomly selected. So any W, any weight selected here will intersect somewhere on this parabola. Now, the loss function is at minimum at this point right here, right? And this is the loss function is higher or is increasing as W is increasing or as W is decreasing this way. But at this point, we really want to get the loss as close to this point as possible. So we start somewhere on this parabola by selecting randomly the weight. And then we want to move closer to the minimum value of this loss function. How do we do that? We take steps. And this step right here might look large. In reality, it's smaller. I made it large here to illustrate this concept better. We take step. The step is eta times the derivative. So the derivative on this side is positive. The derivative on this side is negative. And if you think about it, if you're moving up this way, you are increasing the weight and increasing the loss. The derivative is positive. If you're moving down, the weight is decreasing and the loss is decreasing. So the derivative is still positive. But here, if we are moving down, the weight is increasing, the loss is decreasing. So the derivative is negative. But if we're moving up, the weight is decreasing, but the loss is increasing, so the derivative is still negative. So anywhere past this point going this way, the derivative is negative. Anywhere past this point going this way, the derivative is positive. So to move down from here, Or to move down from here, we're going to do exactly the same thing, apply this equation to find the next value of the weight. It's the initial weight minus the step, which is eta. It's a constant that we select at the very beginning of the training. Multiply the step by the derivative. The derivative is going to be changing as we get closer to zero. At zero, at as we get closer to the minimum value of the loss, at the minimum value of the loss, the derivative is zero. So at that point, if we get W at this point, we basically got the actual output exactly the same as the predicted output defined by this process. So the next W here, visually you can see it's the initial W minus the training rate or the learning rate times the derivative. It's the same equation even if the initial W is on this side of the parabola. Now you can imagine if the learning rate, eta, is large, we may miss the minimum value of the loss function. So we may skip. So if we may start somewhere here, and if the learning rate is too large, we may jump over here. And then when we jump over here, we come back this way, depending on the number of epochs, basically the number of iterations that we are executing this equation. And if the number of epochs is if the number of epochs is too small and the learning rate is also too small, we may never get to the minimum value of the loss function. So what we described here is really the gradient descent, meaning you can see that we are really going down on this side if the initial value of the weight on this side, then we are descending. Or if we are on this side of the parabola, we are still descending to the minimum value of the loss function. So in two-dimensional space, the gradient descent is nothing but the derivative, and we are using the derivative to find the minimum value of the loss function. In three-dimensional space and above, we call it the gradient descent. And it's the method to find the minimum of the loss function. Now, if we take one data point at a time, so let's just say we have 1,000 data points. Each data point has X and Y as coordinates. If we take each data point and apply and update the value of the weight using this gradient descent method algorithm, if we do that for just one data point at a time, the gradient descent is called stochastic gradient descent. If we follow this algorithm for more than one data point at a time, meaning we calculate the loss of multiple data points and then find the weight. We call that the batch gradient descent. So it could be 2 data points, 3 data points, or even the whole set. You may also hear the term mini batch gradient. So mini batch gradient means you're taking 2 data points and then calculating the weight based on these 2 data points, or it could be 3 data points, 4 data points, but it's a subset of the data set, not the whole data set. So stochastic gradient descent is one term. Mini batch gradient descent, so based on more than one data point, and then the batch gradient descent could be for the whole data set.